Up until this point, we have only talked about integrals along a line, first in the one-dimensional case, then along curves. In this video, we will continue and take a look at double integrals and later triple integrals. Then we will focus on how to do substitutions for these. Let us start with an example of where one could get a double integral in real life. Assume that you have a lake with area A lake and a depth h. What is the volume? Here, the volume is simply the depth times the area. But this assumes that depth is constant, which is quite rare for lakes. The normal case is that the depth varies with the position. To solve this, we would have to use the double integral. If we compare with the one-dimensional integral, that was the area under the curve, the double integral will be the volume under the area. Let's draw an example function h of x and y and assume that we want to integrate over the red rectangular region. Remember that in 1D we created a sequence of points for the Riemann sum. In 2D we will instead create a grid of points. Each point will now have an x-coordinate and a y-coordinate. We assume m points in the x direction and n points in the y direction. In 1D, we created a line delta x between the points. Now we create areas between the grid points. Assuming a regular grid, we can define delta x as the step length in the x direction and delta y as the step length in the y direction. The area of one area element delta A is now delta x times delta y. I'm using indices I and j here to indicate that the area elements can be different, just as we didn't need a uniform point distribution in 1D. All that is needed is that the area elements cover the full integration area. Using a similar concept as our Riemann sum, we will now write the double integral as a sum of h of x and y multiplied by the area element for each element in the region. Since we are using a rectangular region, it is more convenient to split x and y and write it as a double sum, where I is in the x direction and j is in the y direction. Now, each term in the sum will create a volume. Let's plot these volumes. With this low number of points, the approximation is relatively poor, but increase the number of elements. Now we see that this will converge to the volume under the graph when the number of elements go to infinity. The next question is, how do we calculate this double integral? First, note that we can change the order of the summation without changing the results, as we still sum over all elements. Next, insert expression for the area element. Now we're going to use the fact that we can solve the inner sum first and the outer sum after. To visualize this, let's go back to the coarse grid to start with. Then let the number of elements in only the x direction go to infinity first. This inner sum is actually the Riemann sum we are used to from the one-dimensional case. Replace it with the integral. Now we have the following system. We have a solution for each of the segments in the x direction using the integral. But it's still a poor approximation of the volume, as we still have few elements in the y direction. Now call the inner integral f of y, and let the number of elements in the y direction go to infinity. The remaining sum is just the sum of f of y delta y when n goes to infinity. This is the Riemann sum again. And we can convert it into an integral. what we get is that we can solve the double integral by first integrating with respect to x and then integrating with respect to y. Basically, we solve the double integral by two 1D integrals. We can drop the parentheses. Update the names in the figure to match the integral. We could also change the order of integrals without affecting the result. Note, when we're using multiple integrals, I will always mark which one it is by writing x equals xs to xe, and similar for y. The whole idea of solving the double integral works well for a rectangular domain, where x and y are decoupled. But what about another region such as this circle? Let us take the simplest possible integral and only integrate dA over this area. First, let us check if our rectangular elements can be used for this area as well. Add them with the coarse grid and let the number go to infinity. Hence, it looks like this could work. But how do we set up the sum now that the area isn't rectangular? Start by the equation for the circle and solve for y. We could now claim that the upper half of the circle has equation square root of r squared minus x squared. And the lower part has the negative version of this. Next, divide the double integral into our two separate integrals. The idea is to let the y integral be between these curves. Hence, we set the equation for the curves as limits to the integral. The x integral should then start at minus r and go all the way to plus r. These limits should cover the entire circular region. Now solve the inner integral. The primitive function is just y. We can then insert our limits, which are the expressions for the curves. We can directly see that both terms are the same and write it as 2 times the expression instead. The primitive function for this one is not trivial, but here we can look it up in the table and find that it is the following. Insert the limits again. These two are 0. Here we are dividing by 0, which gives us infinity. Same here, but the minus gives us negative infinity. Arctan of infinity is pi over 2. Arctan of negative infinity is minus pi over 2. And we can see that this becomes r squared times pi. Which means that we have used a quite complicated way of calculating that the area of a circle is pi r squared. There are of course easier ways of doing this, such as polar coordinates. But the aim was to show how to handle the case where one has a curve as input to the inner integral. Let's move on to triple integrals, which also can be called volume integrals. Let's start with an example again. We have a container with volume V and density ρ. What is the mass? If the density is constant, the mass would simply be density times volume. But what if the density varies with the position? This would create a triple integral where we integrate the density over the volume. These are a bit harder to visualize, but you can divide it into triple sum this time. Here we are integrating over our volume element delta V. we can write that this element has the size delta x, delta y, and delta z. In this initial case, we can assume that it is a rectangular cuboid, and we can write the volume element as delta z, delta y, delta x. When we solve it, we can simply convert it into three integrals, which can be solved one by one. Let us take a very simple case again and just integrate dv over the volume. Our volume will in this case be a sphere, and again we will stick with Cartesian coordinates for now. To match the shape, we can rename it. Again, we need to have limits that vary with the coordinates. The inner integral can be a function of both other variables, the middle only a function of the outer variable, and the outer integral cannot be a function of any of the other two. Starting with the z integral, the lower limit should be the lower surface, and its upper limit should be the upper surface. The equation for a sphere is x squared plus y squared plus z squared equals the radius squared. Solve for z. And insert these limits. Solve the inner integral, which has primitive function z. And insert the limits. This is the same term twice, multiply by 2 instead. Now the z variable is gone and we only have an integral over x and y. This is an area integral, and the area is the purple area you can see in the figure. The function value is the length of a line from the lower surface to the upper surface. As we can see, it varies with x and y. Now we're basically back to our 2D integral over the circle we did, but with a more complicated function. The lower limit should be this orange curve, and the upper limit will be this orange curve. We saw in the previous example that the equation for the curve is y equals plus minus square root of r squared minus x squared. Define k squared equals r squared minus x squared for the y integral. Insert k here. And we have the same integral as in the previous example, for which we know that the solution is pi k squared. Now go back to r and x. We no longer have any y dependence in the integral, and this will be a one-dimensional integral over a line. The line is the green line from minus r to r. The function value will now be the area of the circular disk that we can fit at this given x value. We can see that it varies with x when we animate the path it takes during the integral. Update the x limits. This is just a polynomial. Insert the limits. Same term appear twice. And the final result becomes pi 4r cubed over 3, which is the volume of a sphere. Next, it's time to move on to a slightly more advanced topic, which is substitutions for double and triple integrals. This will be the topic for the rest of the video. Let's do a quick recap of the 1D case, but this time in the opposite direction of what we did in the one-dimensional video. Start with the integral of f of x dx from xs to xe. Now assume that x is a function of t. We can also multiply and divide by dt. And finally, if we integrate with respect to t, we need to update the start and end points to start time and end time. Here, xs is x of ts and xe is x of te. This part is the scaling factor for doing substitutions. Or a small step in the x direction dx is given by dx dt times a small step in t called dt. The issue though is that this trick of simply multiplying and dividing with dt does not really work for double and triple integrals. Therefore, I will show a short motivation of what we actually are doing, which will be needed to understand the multivariable case. Start by making a plot of our x of t function, which is the change of variable we are using. This time, we want to use t as our integration variable, hence, define the sequence from the Riemann sum as evenly spaced in t. We are going to use the same sequence for both x and t. Each point in t will have a corresponding x. Now let us type out the Riemann sum for the original integral with respect to x that we want to solve. In the sequence in our Riemann sum, delta ti is ti plus 1 minus ti. Or we can write ti plus 1 is ti plus delta t. As we use the same points in both sequences, xi should be x of ti. Hence, we can insert this into Riemann sum without changing anything. We still have delta x in the Riemann sum though, but we want to use delta t. Let us find this conversion by starting with that xi plus 1 should be x of ti plus 1. We can insert this expression for ti plus 1. Now let us remember the definition of the derivative. Drop the limit and multiply with the delta t. And reorder. And finally insert it into the expression for xi plus 1. We can therefore see that an approximation for x of ti plus delta t is x of t plus dx dt delta t. This approximation will be important when we move to double and triple integrals. Delta xi is the difference between 2 points in the x sequence. Insert value for xi plus 1. As x of ti is xi, these terms cancel. And we have the relationship between delta xi and delta ti, with the derivative as scaling factor. We can insert this into Riemann sum to get the sum that is over delta t instead. Here we have seen through the Riemann sum by dx dt should be the scaling factor when doing substitutions. We can of course replace delta with the d in the limit when delta x and delta t goes to 0 to get the value for the integral. For the general case, start with the triple integral of the function f. Now assume that all parameters x, y, and z are functions of 3 other parameters u, v, and w. What we are going to do is to rewrite the integral to make u, v, and w our integration variables. To give an example of what this transform could be, let us use the two-dimensional case of polar coordinates. A quick recap. We have the position vector r, which could be given by its x and y coordinate. Also introduce the angle of the vector phi. In polar coordinates, describe the vector using the length r and the angle phi to give the direction. The transform is that x of r and phi is r cosinus phi and y of r and phi is r sinus phi. These expressions are in the same form as our transformation from x, y, and z to u, v, and w, but in 2D. Let us assume that we want to integrate over a circle using polar coordinates. Now let's draw a second plot using phi and r as our axes. If we want to represent a circle in polar coordinates, the radius should go from 0 to r, and phi should go from 0 to 2 pi, which gives the rectangle in the figure. Next step is to introduce our point sequence from the Riemann sum, which will form a grid in 2D. As we want to integrate using r and phi, we distribute the points evenly there. Each point in the r-phi domain will now have a corresponding point in the xy domain, as you see in the animation. Call the step between the points in the phi direction delta phi and the step in the radial direction delta r. Now we will introduce the areas between the points. The animation shows each area in the phi r plot and the corresponding area after the transform in the xy plot. In the phi and r plot, we see that they all get equal rectangular shape, but in the xy plot, the area varies. This means that we will need to add some scaling factor here, just as we did in the one-dimensional case. To mathematically handle this, start by looking at the u, v, and w domain in 3D, or our r-phi domain in 2D. We can now define three vectors. The first one, a1, is the vector delta u, or delta r in our 2D example. The second one, a2, is delta v, or delta phi in our example. In 2D, we can now define our integration element delta a in the r-phi domain as the rectangle shown in orange. In the 3D case, we would need the third one, a3, as delta w. We can now draw a 3D example as well by introducing delta u, delta v, and delta w. These can create a volume delta v, where I use u, v, and w as indices to indicate that it is in the u, v, w domain. However, in our original equation, we used x, y, and z as the variables, and the volume element is written using these. The corresponding area can be illustrated as the orange area in the plot of the circle in the xy domain. Hence, we need to calculate how large this volume, or area in 2D, becomes in the xy system. Since we are going to integrate using u, v, and w, the trick here is to take small steps in these directions and see what vectors we create in the original system. Start by defining the vector b1 as the vector we get when we take a small step in the u direction. This vector will go between 2 points in the sequence, just as the a vector, but this one in the xy plot. Similar, b2 will then be between 2 points in the second direction, as you can see in the xy plot. Let us now calculate expressions for the vectors b. Start by looking at x-hat direction. We take one small step delta u and compare with the original position. Remember the definition of the partial derivative with respect to u. Drop the limit and multiply with delta u. And we can insert it here. Continue with the y direction. Here we do the same, but take a small step in the y function. Just as before, this gives the partial derivative. And finally, the z direction is the same. This means that if we take one small step in the variable u, this is how long we would move in the x, y, and z directions. We can repeat with a small step in V, which gives the following vector B2 using the same pattern. And finally, we get B3 by taking a small step in the W in the same way. Let us look at the volume element in the 3D case. This will give us something like this. We have three vectors pointing in three different directions. These vectors will create a volume element we actually want when we solve the integral. If you watch the vector multiplication videos, you should know that if we want to calculate the volume of a parallel epiped with three vectors as sides, we can use the determinant of the matrix created by the three vectors. Hence, we write delta V is the determinant. Determinants are symmetric, so we can transpose it without changing its value. If we have the term delta U common for all elements in a column, we can place it outside the determinant. Same for delta V and delta W. In the limit when they go to 0, change delta to D. This is the general expression for the volume element if you want to integrate using U, V, and W. The matrix we have is called the Jacobian matrix. It is commonly written using this shorter form. To finish the expression for the substitution, now write that we have a function of U, V, and W. To be strict, I have renamed the function to f, u, v, w here, as while it gives the same values as f, the three inputs are different. Continue and replace the volume element with our expression for the determinant. To illustrate it, I will do one example using spherical coordinates. This means that u is r, v is theta, and w is phi. The transform for spherical coordinates is that x equals r sinus theta cosine phi, y equals r sinus theta sinus phi, and z equals r cosinus theta. Here x, y, and z are functions of r, theta, and phi. I will cover this transform in more detail in another video about spherical coordinates. Let's do a quick visual recap of how spherical coordinates work. R is the length of the position vector. Hence, it's always larger or equal to 0. Theta is the angle between the z-axis and the position vector. Theta is a value between 0 and 180 degrees, or 0 and pi if you use radians. Phi is the angle between the x-axis and the projection of r on the xy plane. This one has a value between 0 and 360 degrees, or 0 and 2 pi. Let us insert all the derivatives. I will do this part relatively quickly as the calculations are quite straightforward. Just watch the animation. Next is to calculate the determinant step by step. Start by these for the determinant, which multiplied becomes 0. Next are these. We can combine the terms. Continue with this. And combine. Now subtract these. And combine. To simplify, Note that these are a common factor. And this is 1. Continue and subtract these, which contain a 0, hence is 0. And finally subtract these. And combine and reorder. These are a common factor. This is 1. These are common. And this is 1. Insert the final part of the expression. This is the volume element in spherical coordinates. There is an easier way of figuring this one out though, by using that spherical coordinates is an orthogonal system. I will show this in future videos. To demonstrate why this is useful, let us show the same integral as we did earlier, but this time in spherical coordinates. Insert the volume element. Let us plot the sphere. Write the triple integral as the integral over r, theta and phi. Integrate over entire sphere. Start by solving the phi integral, which is an integral over a constant and becomes the interval length 2 pi. Let us visualize our remaining integral, which is the integral over a half circle. This term now represents a circular ring, which varies with r and theta. Next, integrate over theta. Insert the limits. Cosinus pi is -1 and cosinus 0 is 1. These combined becomes 4. Now what remains is the integral over the following line. This term is a spherical shell that varies with the radius. Solve the integral. And insert the limits. And we have recovered the volume of a sphere in a way that involved significantly easier integrals than when we used Cartesian coordinates early in this video. This shows how useful it can be to change the different coordinates when we do double and triple integrals. If you compare the two cases, also watch the intermediate steps after we had solved 1 and 2 of the integrals. You saw that these intermediate steps looked quite different, but both options covered the entire sphere and gave the same results. The expressions we have used for substitutions here work for any transform. In later videos, we will talk about orthogonal coordinates, which can be solved in an easier way. This will end this video. Next up will be surface integrals, where we'll see similar ideas as we just used. Thank you.